Hello students, so continuing my lectures on complex analysis, we will discuss about Cauchy's residue theorem today. So before starting that, let us first try to understand what is Lorentz series. So we all know that if fz is found analytic, in and on C a contour, then according to Cauchy's integral formula, any point inside the contour z0, f z0 then becomes 1 by 2 pi I fz z minus z0 dz for any contour C and for any point inside C. Now there is another theorem which is basically called the Lorentz series. It says that if fz is analytic, then we can express fz as equal to integration n minus n infinity to plus infinity coefficient an to z minus z0 to the power n. Now in this series, the value of the a minus 1 coefficient is actually called the residue of the function f at the singularity or at the pole z is equal to z0. Now pole means that the function is not analytic at that point. Now say again if we draw a contour, this is imaginary z and this is real z. This is a contour C, and say you have a singularity z0 here. So it may so happen that there are multiple singularities, say z1. Apart from z0, they can be z1, z2, etc. Now, the any integration inside this contour will be then expressed as the sum of all the residues corresponding to the singular points. It will be sum of the residues multiplied by 2 pi I. This will give you the value of the integral. Now the poles, these poles can be classified into two categories. One is simple pole, another one is not simple pole. Simple pole means say you have a function 1 by z minus 1. Okay, so that means it is singular point t z is equal to 1 because at this point the function is not analytic. So this is a simple pole, but had it been z minus 1 to the power any power k, then it would have been then called a pole of order k. Now, why this is important? Because the residue is in fact different from these two poles. In fact, a simple pole is one of the conditions of the pole. So normally we can express for simple pole the residue is simply equal to limit, see the simple pole is at z0, so limit z tends to z0, z minus z0 into fz. This is the simple pole. But if it is a pole of order k, then the residue is given as at z0 is given as 1 by k minus 1 factorial limit that tends to z0 differential of the order of k and differentiating z minus z0 to the power k into fz. So this is the expression of the residue. Now here for simple pole, of course, the order of k is equal to 1. So if you put the value of k is equal to 1, automatically we get the residue as equal to limit z tends to z0 z minus z0 into fz. So this we have already seen here. So this is one of the cases, special cases of the residue, the pole of order k. Now this residue theorem, Cauchy's residue theorem, we will call it as CRT. This Cauchy residue theorem is used to compute integrals. We will see how. We'll take an example. Suppose you have been asked to compute this integral minus infinity to infinity 1 by 1 plus x square dx. So what we will do, we will transform this integral into a complex integral. We will write that this is actually equal to 1 by 1 plus z square whole square. Now how can we do it? Now what will be the contour for this? So if we draw a complex plane for example real z and imaginary z. The contour we can express it as like a semicircle. So this becomes a contour R, and this becomes a contour C1, and these are actually, you can write it as minus R to R. So these are actually the limits. So R tends to infinity. So the integral is basically equal to limit R tends to infinity minus R to R fz dz. So this is how we can express a normal integral into the complex plane. So the answer will be actually equal to this C that we have written. dc is in fact equal to CR plus C1. But since it is along the axis, so we only consider this CR, that means only consider this semicircle. So this is the normal integral is getting transformed into an integral in the complex plane. So we can easily focus on this. So proceeding. So now we have a integral C. The function is 1 by z plus 1 whole square to dz. Now we have to find the singular points or the poles. For that we have to make z plus 1 is equal to 0. So this is z square plus 1 is equal to 0. So we get two roots plus I and minus I. So out of which this is only the pole, but because this is lying outside the contour, if you look back, so there is nothing in the negative axis, so we will not consider the minus I to be inside the contour, we will only consider the plus I. So we have this is the only residue. Now we have to find the this is only the pole, and this is a pole of order k, because you can see that there is a power associated with it. So order k is equal to 2. So the residue at I is simply equal to limit z tends to I d by dz of z minus I whole square into fz. Now this z minus I whole square into fz is basically equal to z minus I whole square, and we can write 1 by z square plus 1, so this should be 1 whole square as 1 by z plus 1 whole square into z minus 1 whole square. So these to cancel, so we ultimately get 1 by z plus I whole square. So the residue is now limit z tends to I d by dz of 1 by z plus I whole square, and this is again equal to limit z tends to I minus 2I z plus I whole cube on differentiation, and if you put the value of z, it becomes minus 2 plus 2I whole cube, and that is equal to 1 by 4I. Now the value of the integral is from the theorem, we know that it's 2 pi I into sum of residue, since we have only one pole and so only one residue, so it will be multiplied by 2 pi I only, so it's 2 pi I into 1 by 4I, and so answer is pi by 2 is equal to minus infinity to infinity 1 by x squared plus 1 dx. This is the value of the integral.